Let's have a look at the syllabus first. This
Yes.
topic 7 will cover the three smaller subtopics. The first one is discrete energy and radioactivity. This is the description of the understanding, the knowledge, and some skill, utilization and arms that you need to achieve. That's the first subtopic. The second subtopic is nuclear reactions, radioactive decays, alpha, beta, and gamma decay. And third subtopic is the structure matters, including the two families, hadrons and leptons. The hadron family includes two smaller classes, which is baryons and meson. We'll study those things later. For about 30 minutes, I can only help you to recap the basic of the first subtopic about discrete energy level and probably a little bit of radioactivity. Okay. In the earlier time in the 19th century and the beginning of 20th century, the scientists and physicists thought that energy is continuous. It is like a flow of water from one place to another, from one system to another system, like the flow of water continuously. We can have any value of energy, okay? But after doing some research about the new phenomena such as emission spectrum, absorption spectrum, the transfer of energy in form of radiation from an object that is heated up to a temperature, very high temperature, emission spectrum. When we heat up a type of gas such as helium to a very high temperature, there's some type of machine, some kind of lamp that contain a type of gas such as helium or mercury or neon, okay? And we use electric current or the normal source of thermal energy to heat it up to a few hundred centigrades or even 1,000 centigrade. Then that hot gas will emit some light, okay? And then that light is allowed to pass through a prism, a spectroscope. Let me show you a video experiment. After passing through the spectroscope, we will have this emission spectrum, which is some line of colors, lines of different colors on a black background. Okay. Emission spectrum experiment. Yeah. For some normal light bulb like this one or the light bulb that we usually use in our homes, these light bulb emit kind of like almost white color light, very similar to the color, the light of the sun. Okay, and therefore when the light passes through a prism, a diffraction grating, or a spectroscope, the spectrum is continuous like rainbow, like these rainbows spectra. Okay, but if we use another sort of light, which is like this light bulb containing some kind of noble gas, what is it? Probably neon. Let's see, mercury. Okay, mercury vapor in this lamp. Then this mercury vapor will emit some kind of light which is not continuous, not like rainbow. And after passing through the spectral, no, this is nitrogen spectrum. For this mercury spectrum, this is a spectrum with the blue line and green, kind of mix between green and yellow here, huh? And green. This is the spectrum, emission spectrum of this mercury gas light. Okay, mercury emission spectrum. As well as studying many other phenomena. Okay, this is the spectrum of mercury, a little bit similar to this real experiment, right? You see the colors, cyan and green and yellow. Okay.
Yep.
As well as studying many other phenomena like photoelectric effect, which we'll study later. It was discovered by some scientists like Niels Bohr that energy turned out not to be continuous, not like a flow of water, but like a flow of particles instead, meaning energy is discrete, not continuous. Energy can have the smallest elementary value, just like the electron, the elementary particle carrying a elementary charge, which is minus 1.6 times 10 to the power of negative 19 coulomb. Okay, so a beam of energy, a certain amount of energy, is actually a bunch of trillion particle containing energy, and those particles, packets, okay, are called photon. It is not a material particle, not a matter, but it's like imaginary particle carrying energy. Okay, so energy is discrete, not continuous, containing by the beam of photons. Okay, the energy of one single photon is calculated by this equation, E equal hf. Okay, where h is the Planck constant. Here, Planck constant. The value of the Planck constant is 6.63 times 10 to the power negative 34 joules second. This value is given in the data booklet that you use usually for solving problems. Okay, Planck constant discovered by Max Planck, the scientist in the beginning of the 20th century, at the same time with Niels Bohr. Okay, f is the frequency of the photon. So it is kind of strange here because frequency usually associated with a wave. We have an oscillation. We have a pendulum oscillating back and forth, and frequency is how many oscillation per second. But for a photon, we also define its frequency similar to a wave. Okay, and use the wave equation. The wavelength lambda is determined by the speed of the object, the wave, which is for the light, the speed is c, 3 times 10 to 8 meters per second. Okay, lambda is the speed c divided the frequency f, and therefore the frequency f here is the speed of light c divided lambda, the wavelength. So here are the two equations that you're gonna use to answer some question in the first subtopic about discrete energy here. Okay, and in the booklet, let me find the booklet here. Here, those two equations are given. Yeah, energy of the photon, hf or hc over lambda for the energy. Okay, are you still listening? Because I don't have any response.
Oh yeah. I'm still listening.
Okay, I usually ask other students. No, okay, so that I want to make sure that they understand what I'm explaining.
Good.
Okay, this equation tells us the higher the frequency here, hf, the higher the frequency of the radiation, the higher the energy of the photon. The energy of photon is inversely proportional to the wavelength. The longer the wavelength, the higher the shorter, the lower the energy. Sorry, long wavelength, lower energy here. The next topic is atomic energy level. The energy of the electron in an atom is not arbitrary, it's not continuous. The energy of an electron cannot have any value possible, but each electron can have some specific energy level. It is like climbing from different floors in a building, first floor, second floor, third floor, etc. And the energy levels of each electron depend on the type of element. It is hydrogen or helium or sodium or mercury. Okay, meaning each element will have different, distinct, specific energy level, like a fingerprint of our people, human. For example, this is the energy level of hydrogen. The lowest energy level is minus 13.6 electron volt. It is called the ground state. There's a principle later that we we'll look a little bit through because it's not involved in the curriculum. It's called the Pauli exclusive principle, which states that the electron tend to occupy the lower energy level first, filling those energy level, and then all the electron will occupy all the higher energy level later. And therefore, we have the model of electron orbiting around the nucleus with different energy level. Atomic model energy levels. Yeah. Like the electron will occupy the first energy level, which is closer to the nucleus first, and that level can contain 2 electrons, which is called the K level. Okay, the second level, called the L level, can contain maximum 8 electrons. Okay, and the next level, M, can contain maximum 18 electrons, and so on. And in an atom, the electrons tend to occupy the lower level closer to the nucleus first, before other electrons outside occupying other levels. Okay.
Okay.
And very important that this is just a model. It's not the real reality, because the real thing in reality is very complicated. We cannot define the exact position of electron in the atom. We can only calculate the probability that the electron can appear in certain region, certain area in the nucleus, forming a electron cloud called orbital cloud. Orbital cloud, cloud of electron. But the real thing, the modern model here about the orbital cloud of electrons are very complicated and only used for students at university or when you study higher, like PhD and master, etc. Okay, we're learning only the simplified model of energy levels like this.
Got it.
When an electron transfer the energy level, what's it called? Transit from one energy level at higher energy level, for example, the second excited state of energy level to the lower state. Of course, there's some valence space there that the electron can move to closer to the nucleus, having greater magnitude of energy, which is 13.6 electron volt here. The transition of energy level of one electron like this will emit a photon, and the energy of this emitted photon is exactly equal to the difference in the energy levels from between the first and the second states, meaning the energy of the photon here is exactly equal to 13.6 minus 3.4. Okay. 13.6 minus 3.4. Or if the electron transits from the third level to the second level, then the energy of this emitted photon, represented by a wave here, is equal to 3.4 minus 1.51 electron volt. Okay. So the length of each arrow here also represent the difference between the energy level, which means the shorter the arrow represent the lower energy of the emitted photon, and the higher the energy level, you see that the energy difference between the first level and the second level is a lot greater than the energy difference between the third and the second levels, and so on. In the fourth and the third order, the energy difference here between these two levels is even smaller than other arrows differences. All right. Work example. So we can do some work example here on this website as well. Here, click here. Yeah, from the easy question to medium and to hard. Okay, sometimes it contains like a dozen or even 20, 25 questions. So that is the start of the learning process, from the easiest step to the higher level, and finally practice with the past papers. Okay, now let's try with the easy level first. Question 1 here. Please read it carefully and tell me which answer option you choose.
All right.
The correct definition of excitation of electron.
Would it be D?
D. Electron given enough energy move energy level sometimes leave the atom. When the electron leaves an atom, it is no longer called excited state or excitation. It's called ionization. Ionization. So the correct answer is C, not D.
All right.
Because it is when electron can occupy higher energy level, be it the ground level, the first level, the second level. So electron can occupy the third, the fourth level, and so on, as long as it doesn't leave the atom. Okay, because leaving in the atom is called ionization, not excitation. Okay, the answer is C.
Okay.
Question 2. The diagram shows energy levels in mercury atom. Which transition produces a photon with the longest wavelength? Do you remember the equation for the energy photon that I have just explained?
Is it H
C
times
over lambda?
All right.
The question is the longest wavelength. So what happens to the energy of the photon?
Does it get larger?
According to this equation, the energy is inversely proportional to the wavelength. The longest wavelength is associated with the lowest energy.
Lower. Okay.
The minimum energy, lowest energy, represented by the shortest arrow among these arrows of the transitions. And so the answer is?
It will be.
Which one
D.
among these 4 arrows is the shortest?
Is it D?
Yes, this is the shortest. That is how to solve this problem, huh?
All right. So D is like the longest wavelength, right?
Yeah, exactly. Shortest arrow indicating lowest energy, but the wavelength is the opposite, longest.
Got it.
Do you need to like taking note? I will take a screenshot, put it on the board here, and export the PDF file. I think I should do that. Yeah. I'll take a screenshot here. The board here. Okay. Question 3. The diagram shows an energy level diagram for hydrogen atom. These are the values of each level. How many discrete photon energies could be produced from these energy levels? How many transitions that can happen between these?
Like how many possible combinations? Is this what
Yes.
this question is asking? Okay.
Okay. Photon energy is produced when there is a transition from one level to another level, to the lower level of one electron in an atom. For example, this arrow represents the transition from the 4th level to the 1st level. So how many combinations? Yeah, you're right. Or how many transitions represented by drawing different vectors, different arrows. This is one transition. With a second transition. Yeah, this is the 3rd transition. As long as these arrows are different from each other, the method is drawing from higher level to the ground state first, ground state. Okay. Then not only that, not to the ground state, but the transition can also occur from higher level to the 2nd level here, or from the 3rd level to the 2nd level also. Is there any other possible transition? No, we cannot find. Oh, wait. One more possible thing here, from this higher level to the next level, right beneath it, huh?
Yes.
Yeah, so there are 6 arrows, 6 different arrows. So the answer is 6.
Okay.
Take the screenshot. Put it here first. We'll arrange the things later. Question 4. Because I have an account, so I can download the PDF and answer.
Okay, thank you.
Which of the following is not a feature of an emission spectrum? I didn't explain the emission spectrum, but have you learned that in school? Emission
I
spectrum
have.
property.
I
Okay.
think so.
So what do you remember the features of the emission spectrum and which one is not the feature? Not.
Okay, I'll just take it. Yeah, let me just read it quickly.
Yeah. Not necessarily to be quick. Deeply learn and understand it. We're learning, not running in a test. Oh, and which school are you studying now?
I'm currently at Ishmik.
IXMIC?
Ishmik International School, Ho Chi Minh City.
Yeah. You to teach some student there, but not this year.
I see. I think it is the not a feature is B, right?
Let me read it. Emission spectrum contains a set of discrete wavelengths represented by
Oh, I
color
mean D. Sorry.
D. Consider of continuous spectrum containing, yes, this is the continuous spectrum, not with dark line. Okay, with dark line on continuous spectrum is called absorption spectrum.
Okay.
One of my excellent students, like 2 years ago, he's an Indian person who, let me check his name. That's 2 years ago, so I forgot it. You know Thảo Lam?
I'm quite new to Ishmik, so I don't think I know like the old seniors here.
But you are like grade 13 now, so
I'm grade 12.
yeah. Thảo Lam is one of the excellent characters there. She got in Oxford.
Oh my God. Okay.
And a Indian student that I was looking for, his name Shaksham. Okay. Answer for question 4, that is D. You chose correctly. Good. Question 5. Larger version of hydrogen emission spectrum from the infrared to ultraviolet region looks as follows. Fun series, bracket series, read person series. If you remember, just answer it first and I'll explain later if you answer it incorrectly.
I would take a guess here and choose bracket series.
Which one?
Bracket series, which is C.
C. Bracket series. The question is the highest energy photon being emitted, and you can see on this diagram, this is infrared, meaning the wavelength is longer, and invisible light in the middle, and ultraviolet having a lot shorter wavelength, and the equation for energy photon is E equal hex C over lambda. So the question is higher energy is maximum, so the lambda must be the shortest, meaning the answer is the Lyman series.
Oops, okay.
In accordance with the ultraviolet light. Okay.
Okay.
Take a screenshot as well. Lyman series. Let me also show you a diagram about these these series. Hydrogen emission spectrum, Lyman series. Okay, here. the transition can happen from higher energy level to lower energy level, and where an electron transits from these higher level to the lowest level, the first level, which is called the ground state. Okay, the transitions are represented by the longest arrows, meaning the energy differences between these levels are the highest, right? So this transition corresponding to highest energy differences is called the Lyman series. The next series is Balmer series. In accordance with the transition from all the higher level to the second level, you see the destinations of these arrows, the red arrows, is to the second level, where the destination of these green arrows is the first level. Okay, so the next series Balmer here is to the second level. The Passion series is from other level to the third level, the green arrow, you see, and so similarly with other series. So the point is that for the destination, the lowest energy level that the electron transits to, they have different names, different properties, or according to the name of the scientist who discovered that, these people, Lyman, Balmer, and Paschen, etc.
Okay.
One more question, and then we can move to the math part.
Got it.
Okay. Isotope, I didn't explain about decay, but we can do a quick question here because it is the easy part. Easy, but not actually very easy. Yeah. Isotope of, I don't know the name of this element, just AM, call it 95, 241. What does it mean by these two numbers, 95 and 241?
95 is like the atomic number, which equals to the amount of protons within an element.
Exactly. Yes.
241 exactly. is like I think it's like the nuclear number, which is like the number of the proton plus the neutron together.
Exactly. Okay. And this element undergoes alpha decay, which later on the proton and neutron number graph represents the correct proton-neutron product of the decay.
I think it's C.
Let's see. Can you explain that, please?
Because when an element undergoes alpha decay, it's gonna emit an alpha particle, which has the same like property as a helium element, which is which has a proton number of 2 and a nuclear number of 4. Therefore, we subtract 4 from the neutron to subtract 2 from.
Yes.
But then we subtract 2 from the atomic number.
Yeah, exactly. An excellent explanation. 240 subtract 4, 237. And then subtracting 237 from 93 by 93 for 1, huh? Yeah. Okay. So that's it. You see the teaching method and the process. We will go from easy quiz to medium to hard. Some practice exercises in some textbook like this or these, and finally the past paper.
All right.
We can easily find the past paper, right? I already have the collection of all the past paper, even the most recent one in May, this May.
Ooh, yes. Okay.
Yeah. So really for the physics part. Now let's move on to the math part, but please excuse me for 1 minute. Need to go to the bathroom.
No, sorry. All good.
Yeah.